Okay, and I do have a bit of a cold, so sorry if I sound bad. Okay, so you know, we're late to the game, but we are working to support Wayland and Mir and you know, provide the general building blocks that are needed for alternate window systems. So I'll talk a little bit about the work that NVIDIA's been doing for that. I mean, it's probably a lot of the things are very obvious to many of you, so sorry if it's old news. But I think bringing a non-Mesa based OpenGL and EGL implementation to the space, you know, brings some unique perspective. So hopefully that has some value to share. And the goals for our work are obviously, you know, so that NVIDIA can plug in to these alternate window systems in the same general manner that Mesa-based drivers do. You know, really, at the end of the day, what end users want is to be able to run, you know, NVIDIA users want to be able to run Wayland compositors on top of NVIDIA's driver. So we're working to support that and continue to leverage NVIDIA's cross-platform proprietary driver implementation. So I'll talk a bit about the different pieces that we've been working on, and then I'll also offer a proposal for an alternate way using a set of EGL extensions to solve some of the problems that are today solved with GBM. So first, DRM's KMS API. So we're in the progress now of refactoring a lot of our display programming code such that that code can be hooked up to the DRM's KMS API. So similar to today, how NVIDIA's driver registers with DRM as for purposes of prime support, will also register with DRM as with the driver mode set flag, so that mode set requests can get passed through to us. So once this mode setting refactoring is done, we'll plug into that infrastructure, and then, you know, people using the basic DRM-KMS ioctls, you know, like the video mode setting support now merged into the Core X server, and then other KMS clients ought to work on top of NVIDIA's driver implementation. It may be worth noting that currently our plan is for our proprietary X driver to not use the KMS API directly, but call through a proprietary interface, you know, so that configurations today where the NVIDIA driver runs that don't have DRM-KMS continue to run. But the same core refactored mode setting code will be used in either case, and it's just different APIs to get to it. And my excuse for this taking so long is that like the mode setting part itself is easy, but it's all the other features that we support, the G-Sync for our variable refresh rate, and frame lock and SLI and stereo and so on. That refactoring all of our code to still account for all of those things, not introduce any regressions there and anger workstation customers. That's really been the hard part. So then the next piece, of course, that we need is an EGL implementation that runs outside of X Windows. So it may be worth noting that starting with Tegra K1, I think, well, yeah, I guess that's the name that we use externally. Tegra K1 uses the same graphics core as our discrete GPUs, and so we're now using the same OpenGL implementation and EGL implementation between our discrete GPUs and Tegra. So last fall we released, started shipping an EGL implementation that still depended on X, but releasing that EGL implementation with our discrete GPU driver. And this fall we'll be releasing an EGL implementation with the DGPU driver that doesn't rely on X. That'll be in release 346, which is our next release cycle coming up later this fall. The KMS support is not complete yet, so while users will be able to get EGL without X, they won't actually be able to use KMS in that release cycle to be able to display it. So okay, so great. So we'll have KMS and we'll be able to use EGL without X. But then the one other piece needed to fit that all together is a mechanism for bootstrapping display with EGL. And I'll get to that a little bit later in this slide deck. So the work that we're doing to support Wayland clients, or the client side of Wayland, So Wayland clients need a way to be able to create an EGL display from a Wayland display object, and need to be able to create an EGL surface from a Wayland EGL surface. And so the Khronos platform Wayland and platform base extensions provide a way to do this. And so from the pseudocode here, you have your Wayland display, and you specify that that's a Wayland, or that's the platform is of type Wayland. And you pass that in to get platform display, and you get back an EGL display. And then getting an EGL surface is a similar sort of API. And then the older, now considered legacy, but the traditional way of doing that was passing in the Wayland display directly as the native display type to EGL get display. And so NVIDIA's driver will support both of those mechanisms to get an EGL display that is talking to a Wayland display. And so then the next thing that an EGL implementation needs is to be able to recognize that that the EGL display that gets passed into it was created with respect to a Wayland display, and recognize it as Wayland specific, and then do whatever Wayland specific tasks are needed. So that's in development. And then then also the client side EGL needs to coordinate with the instance of the EGL driver loaded into the Wayland compositor for purposes of buffer sharing. So that implementation is in progress. And one thing that's sort of interesting about the way we implemented it was that we tried to split out the platform-specific handling of Wayland into effectively a plugin for our core EGL implementation. And that was done so that if there are other platforms in the future, Mir as an example, if we standardize that plugin interface potentially across EGL implementations, then we could allow people writing alternate platforms to implement their own EGL client-side specific handling, and then not burden the core EGL implementations. So I think that's just an idea at this point, but it's sort of interesting. Okay, so then for supporting Wayland compositors, we need the Wayland bind Wayland display extension. And so that provides two basic things. So first, the compositor uses that extension to take a Wayland display and bind it to an EGL display. And then the EGL implementation is expected to register an extension with Wayland that's advertised to Wayland clients, so that the EGL implementation in the client can negotiate with the EGL implementation in the server, or in the compositor, and coordinate for purposes of buffer sharing. And then the bind Wayland display extension also defines a way to create an EGL image from a Wayland buffer. So the Wayland buffer is passed, Wayland buffer handle is passed back and forth, and then in the compositor, create an EGL image from that, and then be able to use that as a texture. Okay, so we implement all those pieces, and then the one interesting piece that's left is what's currently provided by GBM. So GBM today is used by compositors to fill several things. So first of all, it's used for bootstrapping X-less EGL. So whereas in a few slides ago I talked about EGL in the Wayland client creates an EGL device, an EGL display from a Wayland display. Obviously we can't do that for the EGL loaded in the compositor because we don't have a Wayland display yet, so it's bootstrapping. In the next slide I'll give an example of that, but GBM is used as the platform from which to create an EGL display in the compositor. GBM is also used as the mechanism to import buffers from the client, and it gives the compositor a way to name the buffers which should be submitted to KMS to be displayed. So based on some of the conversations we had last year about, James Jones from NVIDIA gave a presentation last year on some ideas he had for EGL device and EGL output extensions. based on the conversations we had around that, the next few slides will present a different way to fill the pieces that the GBM provides. And then I'll explain why, from NVIDIA's perspective, we think that's a better way to do things. So first of all, so here is typically how compositors bootstrap EGL inside the compositor. So get a file descriptor by opening a DRM-device file, pass that file descriptor into GBM create device. Now you have a GBM device, and then pass that in as the native display type to EGL get display. And so then from there, the EGL implementation is expected to recognize that that GBM device is of type GBM, and then create an EGL display from it and go from there. So the EGL device object that James talked about last year, we've spec'd out a few extensions to handle that. So the first of those is something called EXT device and so the pattern with all of these extensions is that there's a base extension that defines the basic semantics, and then extensions that allow you to do interesting things with that base functionality. So in this case, the device base extension gives you a way to enumerate the devices in the system, the GPUs in the system. So you call EGL query devices, and you give it an array of EGL device objects, and then it populates that array, and now you have a set of EGL devices, and then you can query interesting things from those. Though this base extension doesn't define what those interesting things are. Stuff that may be interesting would be maybe the PCI bus ID, maybe corresponding device IDs for CUDA or OpenCL, maybe the OpenWF device ID, or in the next slide, the DRM device file. So the next extension is device DRM. So using the previous extension, you can query the EGL devices in the system, and then from there, use this extension to discover what DRM device, if any, each EGL device is talking about. So use that to query the DRM device file, and now from there, you can go do interesting DRM things with that. Oh, and I guess the other important part here is that the EXT platform device extension lets an EGL device be the object, the platform type that's passed into to get platform display. So even without DRM in the picture, you can query the EGL devices in the system to get names for those GPUs, and then create an EGL display from those EGL devices. And now you have an EGL display that you've bootstrapped without talking about anything other than EGL objects. So just like EGL device gives you a way to name GPUs in the system and then correlate them with other APIs that also deal with those GPUs, EGL output does the same thing for display-related objects. So the EXT output base extension defines several new EGL objects, the EGL output layer and the EGL output port. So output layer conceptually is the input to the display engine. It's the set of pixels that will feed into the display engine. And then output port is what's going to be streamed out of the display engine to a monitor. So in KMS terminology, the output layer might be would be a surface, and then the output port would be a connector. And so the EXT output base extension gives you a way to enumerate what outputs there are, and then also to query set properties on those objects. And so then we have extensions built on top of output base that allow you to correlate those display objects between EGL's API and other APIs. Most interesting here is to correlate with DRM objects. So the EXT output DRM extension lets you correlate your EGL objects with DRM-KMS planes. So each KMS CRTC or KMS plane would map to an EGL output layer, and each KMS connector would map to an EGL output port. So you can either enumerate the EGL objects and then query their correlation, or you can basically filter when you ask for the EGL outputs. You can say, just give me the EGL output layer that corresponds to a particular CRTC, or give me the specific EGL output that corresponds to a particular KMS connector. So here's an example of that. So the attribs the layer attribs list here says I want the DRM plane with this ID, and then passes that into get output layers. And then similarly, the port attribs says I want the EGL port that maps to this particular DRM-KMS connector, and then get output port goes and finds that one. It's okay. So using the extensions I've described so far in EGL, we can correlate objects between these different APIs. We can use DRM-KMS to set modes, and then map what objects in EGL talk about the different devices and KMS properties, or KMS objects. Those EGL extensions are pretty straightforward to implement. But so far, we've not solved how to actually present content from EGL through those objects. That's where we get to EGL streams. So a little bit of background on EGL streams in case you're not familiar with it. So there's several EGL Chronos standards that define a new object in the EGL spec called the stream. So it's a flexible mechanism for describing how to transfer frames between a producer and a consumer in EGL stream terminology. So an EGL stream isn't useful until you connect it to a producer and a consumer. Similar to how the device and output base extensions defined some base objects but didn't really define how to do interesting things with them until you had additional extensions layered on top of it. The streams are sort of similar. The basic EGL stream object extension defines the basic objects, but relies on additional extensions to actually define producers and consumers. So by default, EGL streams operate like a mailbox. You just have a single entry in it, and a producer, whenever it produces a frame, overwrites the content in that one mailbox slot, and then the consumer, whenever it consumes from the stream, just gets what's most recently been put in the stream. There are additional extensions to make streams behave more like a FIFO, and you can configure the depth of it and configure and other properties like that. I guess configure the behavior when the FIFO is full or empty. You can also, with the stream cross-process extension, have your EGL stream consumer and your EGL stream producer in different processes, and name those producer and consumer. So the example here is you create an EGL stream in one process, you get a file descriptor that corresponds to that stream, use a Unix domain socket to pass that file descriptor to another process, and then that process can get an EGL stream handle from that file descriptor that corresponds to this one EGL stream, and then create a producer and a consumer in those separate processes. And then there are a bunch of additional EGL streams extensions in sort of the specification stage now to make them more flexible, to do things like be able to bind multiple consumers to a stream, to be able to dynamically toggle who's consuming a stream, dynamically resize the dimensions of a stream. And I mean, the EGL extension mechanism makes this sort of thing pretty easy to extend. So an example producer would be an EGL surface. So using the Chronos Stream Producer EGL surface extension, these names get awfully long. You can create an EGL surface that is the producer of a stream. And so then whenever you call swap buffers on that EGL surface, the contents of that surface are what's are made available to the consumer of the stream. On the other side, GL texture is a example stream consumer. So you can associate an OpenGL texture with an EGL stream, and then when you use it, you lock around its use, and then the contents that the producer is delivering into the EGL stream is what the texture gets to use. Streams may seem a little complicated, but from a driver's point of view, they do have a few desirable uses. So first, they explicitly define who's producing content and who's consuming that content. In the next few slides, I'll go into why these things are desirable. Streams define explicit handoff points between the producer and consumer. In the EGL surface producer example I gave, swap buffers is the clear point where the producer is done with that frame, and now it's being made available to the consumer. And it also gives some encapsulation. So why are explicit producers and consumers good? So from the driver's point of view, we have to make a lot of decisions about memory format and additional resources and how we allocate memory. And the more we know about how that memory is going to be used, the better decisions we can make about tiling format and all those sorts of things. If we don't have that sort of information, then a driver potentially has to assume the worst case. Maybe drivers should be clever about dynamically reallocating surfaces with more optimal memory format on the fly based on the usage, but that gets complicated and error prone. And then why are explicit transition points good? So when a surface handoff is known, then the driver can resolve anything that needs to be resolved between the producer and the consumer. So there may be synchronization requirements. Laurie talked earlier this week about explicit synchronization and explicitly defining when the producer is done with something and when the consumer is going to start using it. Also, there may be cache coherency requirements, and so a clear handoff point gives us a clear point in time to resolve any needed coherency. So one example of this, I'm sure lots of hardware has examples of where explicit transitions would be useful. But with NVIDIA hardware, we have something called color compression, and that reduces memory bandwidth a lot. Rather than, if it's a solid color, rather than write that solid color to the entire surface, write it to, well, it's a complex protocol, but you don't have to write that same pixel value to the entire surface. Our 3D engine knows how to interpret compressed surfaces. Our display engine doesn't. And so if there's a clear handoff between, we've rendered to this thing, and now display is going to consume it, that's the opportune time to decompress the surface. If we don't know who's going to consume the surface, then we have to assume that it might be someone who doesn't know compression. So then we have to decompress. And the decompression is expensive, so we'd like to not do it if we don't need to. And yeah, so if we know both the producer and the consumer, and we know the handoff point between them, then we can make optimal use of the hardware in terms of only doing the minimal amount of synchronization and resolving coherency that we need. And then encapsulation is good. I mean, it's always a balancing act. On the one hand, obviously, we want to provide APIs that are low level enough that an application can use that API and do all the things that it needs to do. But on the other hand, we want an API to be high level enough that that the implementation behind that API can make hardware-specific decisions and not place a lot of burden on the client, on the user of that API having to know, well, different implementations of this API will behave differently, so I need to do different things in different cases. So an example of this sort of thing where encapsulation is useful is NVIDIA's downsample on scanout. And again, I'm sure other hardware has similar sorts of scenarios. But with NVIDIA hardware, when we're performing multi-sampled rendering, someone has to downsample those pixels down to the pixels that the user will see. We can use a 3D engine to downsample, but in some cases, the display engine can actually do the downsampling itself. And there's a performance advantage in some cases to using the display engine. But if we don't know who the consumer is of that surface, we don't know. If we don't know whether or not it's display, we don't know that display. We're basically forced to have to downsample. But if the API is structured in a way that that all of that is encapsulated from both the rendering to the presentation, then that gives the implementation an opportunity to take advantage of features like downsample on scanout. Okay, so that was a long aside to EGL streams. To take that back to the EGL device and EGL output objects that I was talking about earlier, the EGL stream producer-consumer semantics, someone's producing a frame, someone's consuming that frame, match pretty well to the relationship of display to scanout in a GPU. So, you know, if we take that same paradigm and apply it with EGL output and EGL device, we get the EGL stream consumer EGL output extension. And so this gives a way to make an EGL output layer. And remember, that's the input to the display engine in EGLs, in these EGL specs. We can make the EGL output layer object the consumer of an EGL stream. And so this to us seems like a good way to bootstrap display of X-less EGL. And so here's some pseudocode to demonstrate what I'm thinking. So first you'd query the EGL devices in the system, and in this case I'm just asking for the first EGL device, and obviously not error checking and things. And so you get an EGL device, and then from there query the DRM device file from that EGL device. Open that and get a DRM file descriptor, then pass that into the DRM mode setting functions to query all the DRM-KMS resources, pick a DRM-KMS CRTC, do all the work to do a mode set on that CRTC. Then next, create an EGL display from, sorry, that should be EGL device, not EGL devices, but create an EGL display from the EGL device that I picked at the top. Do all the work for EGL initialization. Then get the EGL output layer from the KMS CRTC that we set a mode on. Then create an EGL stream. Set the EGL output layer that I found above as the consumer of the EGL stream. Create an EGL surface that is the producer for that EGL stream. Render some stuff to the EGL surface, and then finally call EGL swap buffers on that surface. So the surface is set up as the producer for that stream. So the rendering flows, or the presentation flows from the EGL surface to the EGL output layer and then is displayed. So that's the basic idea from an API usage standpoint. Any questions? No. It's EGL, yeah. I mean, I think if we compared it, number of lines of code to GBM, I don't think it's that much more. Okay, so if we go that far and we use EGL streams as the mechanism to do presentation, we can also use that to use EGL streams as the mechanism to define buffer sharing from Wayland Clients to the Wayland compositor. And so if we were to do that, we could extend the bind Wayland display existing extension and recall that you use that extension to create an EGL, to associate a Wayland display with an EGL display inside the compositor. We could extend that mechanism to be able to query the buffer type of a Wayland buffer. I guess the bind Wayland display extension also deals with relationship of EGL and Wayland buffers. We can extend that extension to be able to query the type of a Wayland buffer. And the type today, the usage is an EGL image. But then we propose an additional extension that adds a new type to a Wayland buffer that could be the the consumer side of an EGL stream. And so if we do that, and the EGL implementation in the client creates makes the EGL object wrapping the Wayland buffer in the client the producer of an EGL stream, then using this mechanism in the compositor, then we can create a texture or whatever consumer object we want from that EGL stream, or inferred from that Wayland buffer. And I should note that all of this is implementation, within the EGL implementation and within the compositor. So this would have no impact on Wayland clients. So, all right, this is like 20-some slides. Why did I go through all this rather than just implementing GBM? And that's a fair question. I think from NVIDIA's point of view, GBM isn't horrible, and we could implement GBM if that's where the community wants to go. I think there's a few small things we'd have to work out. First of all, libGBM is distributed as part of Mesa. We wouldn't want to have NVIDIA just provide a new libGBM binary. We'd be in the same problem as libgl.so. But libGBM, as implemented today from my skim of the code, has a back-end loadable mechanism, and so we could plug into that probably without too much effort. But we think what I've described here is better long-term for the ecosystem. EGLStreams is an open standard. EGLStreams is good for performance, specifically because it defines clear producers and consumers of who's going to be using the buffer and for what. It defines clear transition points so that implementations have clear times to handle synchronization, to handle any coherency resolution, to decompress if we're managing color compression, all of those sorts of things that a driver needs to do. And EGLStreams is portable as an EGL extension. So, for example, you could imagine scenarios where DRM isn't involved at all, and defining some other building block extensions on top of these. We could create an OpenWF display. We'll use OpenWF and do mode setting through that, and get EGL output objects that correspond to those OpenWF objects, and then have do mode set and presentation through that. For example, on a platform that doesn't have DRM, like QNX. And to be fair, what I've sketched out here certainly is not complete. And I've not described anything to sufficiently handle atomic presentation on multiple layers, though I think that would be possible through additional EGL extensions. And we'd have to work out how to do clean handoffs between console and a compositor driving this. Like, right now, the pseudocode I described did a mode set and then later did the first presentation. You'd want a way to be able to specify the content that should be displayed when you first do the mode set. And then also positioning the output layers within the CRTC. The first half of my presentation, I described a lot of the basic work that NVIDIA is doing. So we're going to continue to work through that, continue to refactor our display code, and get to the point where we can register as a DRM-KMS driver. We're going to ship our EGL implementation that doesn't depend on X Windows. We'll provide the device base and platform device EGL extensions. And so those are useful in general for cases where people want to create EGL and render render using OpenGL, outside an X Windows environment. We have customers interested in server-side rendering and aren't concerned at all about display. And so this set of extensions, the first set of extensions I described, would be sufficient to accomplish that. And then the other pieces that I described to provide support for Wayland Client and Wayland Compositor, the platform Wayland and bind Wayland display and those extensions. And then from there, we have prototyped running Weston on top of the EGL output, EGLDevice type model that I described. So we'll get those patches cleaned up and then send them to the Wayland mailing list, to solicit feedback on the idea of it. And so for other EGL implementers, I'd encourage you guys to look at the specs for the EGL extensions I described in this talk. We think the EGLDevice set of extensions pretty simple to implement and have some good utility on their own. So I think there's that would be a worthwhile thing to look at. I know Mesa doesn't currently implement EGLStreams, and that's admittedly more complicated to implement. But I think it does provide some useful functionality as well. So I would encourage people to look at those extension specs. And yeah, so I guess in general, I am interested in feedback on whether or not there's any interest in the EGLDevice plus output plus streams mechanism to manage presentation and buffer sharing. So thank you to a bunch of people who've done a lot of spec work for all these EGL extensions. James Jones has driven a lot of that. Daniel Karch at NVIDIA. Chad Versace at Intel has contributed a lot of feedback. Acorn Pooley was formerly at NVIDIA. He's now off building robots at some other company. And then Christopher James Hulse Rogers at Canonical. And many others have provided a lot of feedback on the spec work. And here's links to some Saturday reading for you. So that, I think, is all I have. Sorry, it was a lot of information, and we're well over time. So comments or feedback?
Okay, so with this, get an EGL stream from a WL buffer extension. So a Wayland buffer is just a one-shot object. It's not a stream of things. So how does, the EGL stream seems to be very, very much a pipe, whereas buffers are a single image. So how does that work?
And so do you, I guess maybe I misunderstand how Wayland buffers work. Do you create a Wayland buffer, you render it, and then you destroy it? Is that a...
You can.
Okay.
You can make a new buffer every single time if you want to.
Okay. And you could create an EGL stream every time if you wanted to, too. So, is the Wayland buffer usage typically single use and then destroy?
I think Mesa right now creates a pool of 4.
But I guess, is it, Wayland buffer is, that's
the natural object for it, I think, for a stream to bind to is a surface, not a buffer, right? A WL surface.
Yeah, so the surface...
the thing that you're going to record multiple buffers being posted to.
Yeah, okay. The surface records, is usually a pool of buffers, but for instance, if all of a sudden the buffer goes full screen and we can scan out, we might destroy the entire pool and we create a new one with a different tiling format. Yeah. Or whatever. So there isn't necessarily a necessarily fixed pool of buffers, and there isn't, a single buffer isn't really a stream of things. It's just a single image. So
yeah, I may have misspoke in the talk then, and yeah, so maybe that the object mapping is not appropriate the way I described, and so maybe a Wayland surface is a more appropriate thing. And so how does a Wayland client manage the buffers? Multiple buffers back in EGL or a Wayland surface?
That's inside your EGL.
Okay.
And then the other thing that we do, at least when we're running on top of DRM, is we can take one of those buffers and there's some DRM code to turn it into what DRM and KMS can use, and then we can just put it directly on the display. So we can take the buffers from the client, stick them directly on the display, and we can do that one buffer at a time. And then, or we can also do it with planes, we can just have one window that's off in its own plane refreshing, and we don't have to refresh the entire display.
Right.
So do we have a way to do that with these extensions? You had the surfaces, but is there a planes concept that we can use? Yeah,
so the EGL output, I think, is it output layer? Sorry, there's too many object names, but one of the EGL objects, and I think it's output layer is the individual plane, and so you could correlate, the EGL output layer that maps to the plane that you want to present to. And so yeah, so you can describe the individual planes that are the input to the display.
Okay, and then are those associated with specific KMS planes?
Yes.
Okay.
Yeah. Yeah.
Just a quick comment on the output DRM extension. With latest kernels, you don't really need an output on the CRTC because we have primary and cursor planes, so it's planes only, essentially, for API design. Depending, yeah, it's kind of pointless to add something that's deprecated.
Yeah, yeah. So
at least for new stuff.
Okay, so just query with respect to a plane rather than any.
Should be enough. At least on recent kernels, if you have user space that says, yes, I can cope with this.
Okay. Okay, thanks for that. All right, any other comments for now? All right, thank you for your time.